Okay, let's learn how to make a free body diagram. Free body diagram. All right. We'll review what we already know, the different kinds of forces. All right. Force of gravity is always straight down wherever Earth is. Okay. The normal force is always perpendicular to the surface that you're talking about. A tension is always along a rope or a chain. The force of friction is always going to be, if you're headed one way, the force of friction is always going to be back the other way. And applied force is everything else that you might even have. Okay, so there we go, different kinds of forces. And we're going to make a free body diagram, which is a picture of all the forces acting on one object. Very importantly, all the forces on just one object. So, that first thing, we're going to list our different forces. We're going to look at a car driving at constant velocity. Constant tells us that it is going to have all its forces balanced, right? So we know gravity is always working straight down. That's no big deal. If it's going at a constant velocity forward, right, there's probably friction coming from behind. All right, and so this is gravity, force of gravity. And then the question is, well, what's making it go forward? So we are going to call that an applied force. And the car is definitely not sinking into the ground, so there must be some force counteracting gravity. And in this case, it's the normal force. And it's straight up out of the ground. All right, sweet, that's one down. A van parked down by the river. It's not headed anywhere, left or right. It doesn't seem to be pushing anything. And so we know gravity is pulling it down. And whoop, and the normal force is pushing it up. And they are supposed to be about the same length because you draw the line about as long as you think the force is. So there you go, up and down. Good deal. A turtle falling out of a tree. Well, we know gravity is pulling it down. So we got force of gravity. And here's the trick. There's nothing else happening. We remember that whole velocity of x thing. It doesn't change. There's no acceleration, right? And so we know that force has to do with acceleration. So there is no other forces on the turtle that's in the air. It's just falling down. Why is it falling? Well, because it was in a tree. Turtles can't, climb trees. So of course they're going to fall out of them. Next one. A rocket accelerating, and the key word is accelerating up into the sky. So what we need to have is we need to have a force going upward that is bigger than all the forces going downward. And everything has a force of gravity downward pretty much, right? And this force up, which I'm just going to call the applied force because I don't know what it is. They're engines or whatever, right? And it is going to be bigger than the force down. And there's nothing really going side to side here, right? Unless there's wind or something we're not looking at. We're just up and down, and it's accelerating. We know that because the length of the up vector is bigger than the down vector, okay? All right. So when we get into more details, if we were summing up the forces, right, the up and the down, we would see that it is not zero, or forces are not equal to zero, however you want to do it. So we add the top and the bottom we have left over. Okay. Next one, a car slamming on its brakes. So again, guess what we need? Gravity. And in this case, it's not flying up in the air or coming down, so I'm going to have that normal force equal. So at least in the y direction, the up and down, the sum of the y direction is going to be 0. Okay, there's no leftovers. But it's slamming on its brakes and it's going forward, so there's probably friction pulling it backwards. And in fact, friction is most of what's going to slow down this car. And so we have leftover, right? We have leftover force this way, extra force in that direction. And so if we would then write summing up the forces in the x direction, you would not equal 0. Okay, and so it's going to be accelerating that way or slowing down. There you go. If you are going forward, you don't have to have an arrow pointing forward, right? He's going forward, but slowing down. So the only arrow is backward. So keep that in mind. All right, shooting an arrow after it's shot from a bow. This is after it's shot, not while it's in the bow, right? So it's in the midair. It's just like our turtle, right? Gravity's pulling it down, and that's it. There's nothing else going on in the air. You could worry about air resistance or something like that, but there's no air yet. We haven't talked about putting air in there. So the only force on it is gravity. And the sum of all forces, right, is not going to be 0 because it's got gravity pulling down. All right, a turtle sliding down a hill at constant speed. Constant speed means the sum of all forces is going to be 0 when we add them all up. So here's where it gets fun. We're going to take our turtle, and he's pulled down by gravity. And what keeps him from sinking into the hill? Well, obviously the hill. But the hill is going to push out at a normal force perpendicular to the hill, right? Okay, great. And now he's sliding down the hill. Well, right now, the way we look at here, the sum of the forces is not 0, right? Because we have the up and we have the down thing. So we have to find a way to make him 0. So if he's going down the hill, right, then there could possibly be some friction pulling up. All right, and between these three together, you can get the sum of all the forces equal to 0, in which case it's moving at a constant speed. If they're summing up to 0, it doesn't mean it's stopped. It means it's moving at a constant speed. And there we go. Not too bad.